interested in that, that is an option. I sent the link in the chat if you want to take a look at that. But people definitely do double majors within engineering. It's pretty difficult, but people do it. Someone asked, how are relationships with professors, as Berkeley is a big university with big classes? So that is true. Berkeley, the CS classes will be pretty big, especially when you start as a freshman. You can easily go by with making no relationships with your professors if you don't put any effort in. If you really want to get to know your professors, you're gonna have to put in some effort. That means going to their office hours and like actually talking to them. So a lot of students don't take advantage of this. So even though the classes are really big, not that many people go to professor office hours. So for example, one of my professors sent me an email yesterday, or sent an email to the whole class yesterday, saying that 3 people had gone to his office hours on the last day he had them. So there's like multiple hundred students in this class and only 3 people went to office hours. So if you really want to have a relationship with your professor, which I highly recommend, you can just like go to their office hours, talk to them. They enjoy talking about things like outside of school and academia. They're just like pretty cool people in general. So it definitely is possible. And with these classes, like you're gonna have a lot of course staff on there. So there's gonna be like teaching assistants and graduate students who are helping to run the class. They'll lead like smaller discussion sections. So you can also get to know them. And they like, a lot of them do interesting research and other things on campus. So it's cool to talk to them as well.
Okay, some of the questions are getting buried. Let me see if I can answer the next few. The credit hour system, I'm not sure. A unit is supposed to equal about 3 hours of work per week, and most normal classes are 4 units. I'd say as a general rule, really depends on what your classes you're taking, but 12 units is considered a quote unquote lighter course load. It probably isn't depending on the classes. 16 units is typically like average, you're taking 4 classes, and then anything above that is a pretty high workload. And what courses would you recommend we take in the first semester? A lot of people take 61A, 16A, and a humanities, and then possibly another tech. If you're an EECS, you will have to take physics or math 53. But don't feel pressured to stick within that guideline. I'd say doing 61A, 16A, and then another course or 2 of your choice. And maybe a freshman seminar or decal.
Someone asked, do you recommend freshman edge, taking 16A or 61A over the summer? That definitely is an option. I think one of the things that's so great about 61A, especially, is that there's a ton of students in the class. So like in addition to being a class, it's also kind of a community where there's a lot of people. You work together with friends on the projects and whatnot. So if you do take it over the summer, most people don't do that. So when you start your fall semester at Cal, you won't have the experience of being able to like work on those same projects with other freshmen. And I think like that is a good experience to like bond with your friends working over these projects. But that is an option. It's just something to think about.
I can speak a little bit more about taking 61A in the summer. So I actually was on course staff for 61A over the summer, and I think if you have time and want to get a head start, it's definitely a great option to take 61A over the summer. The only thing is, because the course is compressed from like 15, 16 weeks into 8 weeks, it is very fast paced. So if you want to take time to like, well, what's a better way to say it? If you are the type of student that would struggle with like cramming so much material into like such a short period of time, it may not be the best option, but the people that teach it over the summer are all really qualified. And like, it's a great class in general.
Someone asked, out of all the programs available, which ones would you recommend? Prep, freshman, edge, honors? I'm not actually I'm familiar with them, but I don't know anyone who's been in prep or freshman edge. I don't think any of us were part of it, so I don't know how much we can speak directly to that. I would definitely look at the website and see. But I don't think we're well equipped to answer that question. Someone asked, how do you take advantage of the makerspace at Berkeley? Okay. So one of the great things about Berkeley is there are a lot of places where you can actually make things. And there's like supplies, materials for you to do so. So for example, there's the Jacobs Hall, which is like a new design and innovation space. It's pretty much like a massive makerspace right next to the computer science building. And within there, there's like 3D printers, laser cutters, workshops, a bunch of different rooms for you to make things. And you can get a pass that lets you like have access to it. I think it's around $50 a semester, which includes some material fees. So it's not too bad to get access to that space. So I would just look up Jacobs Hall. I can send a link in a second in the chat.
Austin, they raised the price to $100 a semester now. But
oh, unfortunate.
it's like training for like everything in there. I've taken a couple classes in Jacobs, which is the building with the makerspace, one of the bigger makerspaces in it. So it's about $100 a semester, but you get access to like 3D printers, what are they called, like CNC machines. There's laser cutters. There's a whole bunch of other stuff in there. And I think, I'm not sure if they have any program. They might have like programming for Cal Week, but you can also just go to their website and they have like a list of all the like stuff they have. And as far as like other maker spaces, I think there's one in Citrus Lab, which is in Siddhartha Dai, I believe, right next to the EE building. And there's also a makerspace in Moffitt, one of our libraries, and I think that one's free.
There's also one in our engineering building, in our electrical engineering building, called Supernode, which is like a student-run makerspace, which is actually free. So you can just go in there. They have 3D printers. They have like a bunch of tools to make things. I've occasionally dropped in there if I like need parts or something, need to work on something. So and that's like a student group associated with it, which is kind of cool. Someone asked, how big are the upper class courses after the first 3, or review sessions after lecture led by graduate TAs? So it really depends on the class. Some of them can be pretty large, but if you pick a more like specific class, like a less popular class, it will be smaller. I haven't taken, does someone who's taken a lot of upper divs? No.
I've taken more EE upper divs, and the classes, I'm not taking a class that has more than 300 people right now, but there are definitely more popular CS upper divs, like 170 is a big example, that are very large, maybe even comparable to a lower div.
170 is often referred to as 70 with a 1 in front of it, just in terms of like the number of people who take it.
I think I'm in 170 right now, which is the algorithms class, and there are 700 students. The other upper div I'm taking, 186, which is databases, has I think 500 students. But sections are generally pretty small, like under 30 students. And as like the semester goes on, attendance tends to drop also. So it's definitely not hard to find like a more intimate atmosphere if that's what you're looking for.
I've been in classes where discussions were effectively office hours by the end. By the way, we are now in theory live. So if anybody can hop on the Twitch and confirm that something is coming across from me, that would be awesome.
Yes, I do see.
Wonderful.
The IPython is a little small. I don't know if you can make that.
Yeah. So I have different screens set up that are supposed to be like able to focus on different parts of it. Is it legible if I do that?
Wait,
Oh,
George, can you mute yourself in the Zoom chat?
not the highest quality. Maybe if you zoomed in a little bit.
Okay, I think I'll try to answer a few more questions as the demo is getting set up, but wait, I'm hearing myself on the Twitch screen. It's a weird echo. Okay, in terms of questions that we have here, figured out that I had to mute myself on the Twitch screen. Let's see, where did we leave off?
Actually, I think we're gonna try to do everything, all the audio over Zoom. Just make it a little simpler. Is that cool with you, George? Yeah, so if everyone could stay on the Zoom for the audio, and then I think we're just gonna have the video on Twitch. It's just like,
I muted myself. Sorry.
yeah, so if you could stay on both Twitch and Zoom, just have your audio for Zoom on, and we'll try and have all the audio through Zoom,
Yeah.
and then just disable the audio on Twitch.
I guess the thing that that I'm concerned about is that the Twitch stream video is a couple of seconds delayed from the audio on the Zoom call. So if it's ever like unclear what I'm pointing at or something, please just stop me and tell me to clarify.
Are you ready to get started?
Ready as I'll ever be.
All right, let's do it.
you guys have more questions, we'll have a panel at 2 with more members of HPN. So we'll answer everything that didn't get answered now right after this.
Well, in any case, now that we are hopefully ready-ish, I'm George. I'm currently I guess you'd call me a senior, but I'm finishing in this coming fall here at Berkeley. And welcome to my Corona bunker. Today we're going to be talking some about electronics and how electronics are used in communications, and like kind of how, like the phrase that I was thinking of when I decided to title this stream is how electronics brings people together. And on that theme, first we're going to be talking a little bit about a very simple optical communication setup that I've built here. And then we're going to be using software-defined radios to listen to some broadcast FM. And so, first off, what's going on here on this circuit board? Oh, pardon me. So here on this circuit board, we've got a very simple setup for doing like a very short, non-coherent optical communications link. And so this microcontroller here is supplying power and control to a light-emitting diode. And so there's a computer underneath this big heat spreader here, which is running the program that's exposing this, this little shell on here. And this shell is controlling that light-emitting diode, that LED. And the control protocol that it's set up to use right now is called pulse width modulation, PWM. And so pulse width modulation fundamentally means that like there's a certain signal in which you want to encode some kind of data. And pulse width modulation means encoding a signal by changing, like, by basically pulsing that carrier signal at some predefined frequency, but changing the fraction of that pulse, which is on versus off, in order to encode some information in these pulses. And so here you can kind of see, hopefully on the Twitch stream, that the signaling LED, which is the red one here, is blinking very slowly. But the software that's running on this board right now knows how to change that. We can go even slower if we want to. And now we wait, and now we wait. Or we can go very, very fast. Hey, I hear somebody's mic. Is somebody trying to ask a question? Well, in any case, by so by doing this pulse width modulation fast enough that the camera I'm streaming from my desk onto is not able to actually resolve those individual pulses, we can create what's effectively like a kind of janky analog output, where we can scale the duty cycle to, actually, you guys will probably be able to see this indicator LED better if I point it at the camera. There we go. And so if we set a duty cycle of 20% now in this pulse width modulation, that means that like for a given millisecond of time over which it's running a period, it's now going to be like up for 20%, down for 80% of it. And so that creates, like, when it's running slower enough, effectively like a pseudo analog output where like we can just directly encode a value into this duty cycle between, say, 0 and 1. And that value then, like I guess I'd say the imperfections from just transmitting that value will only appear at frequencies at least as high as like the frequency of the pulse width modulation itself. And so what that allows us to do is, like, since a lot of systems are inherently limited in like the speed at which they can process things, this LED effectively looks this LED effectively looks like it's just receiving some analog value. Okay, Kathan asks, very cool, but I'm confused about the overall goal of the project. So this is meant to be just like a very simple example of something that modulates data into optics and then can receive it on another end. And so let me adjust things around a little bit. Can you see this little piece here? This is a photodiode. And so what it's doing is receiving some, like it converts the intensity of light that's incident on it into an electric current, which is pulled off these power rails here. And then I have some other circuitry back here whose job is to like take that current and basically decide if take the current flowing off this LED and decide if there's current flowing or not. And so this green LED here is something that I just added as like an indicator, if you will, of like whether or not it's past the decision threshold for deciding if there's light incident on this photodiode here or not. And so on this other end of it, it's connected to a different board over here. And this board is what we're going to actually use to receive this pulse width modulated signal. And so I'm going to switch over to focusing on this Python notebook. And let's see. Yeah. So this microcontroller is currently running a firmware which exposes a Python shell to my computer. And we're going to use it to receive the pulses coming off of this output. Let me actually readjust the circuit a little bit so you guys can see it better. Somebody's asking a very good question. How do you analyze light coming in and make sure it's not just from the surroundings? And so one thing that I set up here is like this potentiometer here allows me to adjust the basically the decision threshold of the output analog circuit. And so let me change the operating frequency down to something that you guys can see happening. And you'll see here that this indicator LED is currently blinking in time with the reference signal that we can calibrate it to coming in here. But this threshold adjustment, and so this integrated circuit here is it's called an operational amplifier, which is currently set up in a comparator block. And so that means that I could use this potentiometer to create some fraction of the potential between ground and the 5 volts reference that this microcontroller is getting from my computer. And some fraction of that difference is used as the value that this circuit is comparing values coming in off the light to. And so if I turn this around a little bit, you'll see that now I've set a threshold that's too high all the time. And now the indicator LED is just not lighting up at all. And on the other side, I can set an absurdly low threshold where this indicator LED is just on all the time. And so this provides just a very simple janky mechanism for me to set a comparison threshold that between the illuminated and dark currents across this photodiode. And by dark, I mean the reference current in the current ambient light conditions.
Hey, George, do you think there's any chance you could maybe zoom in on the circuit board from your phone?
I can certainly try. Give me a quick second here.
Okay. It's just a tiny bit hard to see the actual components on the breadboard. Or even physically move your phone closer if possible.
Let's see. So if I zoom in here, does that do it? Yes, yes, I can. All right, how does that look? Give the Twitch stream a second or so to update.
That looks better. Yeah, that looks good. I think so. Someone also asked what logic gates you're using.
So the only logic gates in this circuit are the ones that are part of these two microprocessors. Inside of this integrated circuit here, like I was mentioning before, it's an operational amplifier. It's an analog circuit, which what it does is it takes the difference of two inputs and then amplifies that by some amount. And it's got a lot of applications that are actually analog. But here I'm using it as basically a digital sense amplifier. So if if this input gets over some threshold, we raise the output decision, and we lower it if it's below. And it's looking on my OBS like you guys can no longer see the Firefox screen capture. Is that happening?
Yeah, we see your circuit board in your terminal and you. We just don't see the Firefox.
God damn it. Sorry, gosh dang it. This is a good, wholesome Christian stream. If I switch focus, no, it's the source that's the problem. Anyways, while I continue to struggle with technical issues, anybody have more questions I can answer?
Someone asked, are we going to be learning how to use a variety of circuits and making circuits like these in our EE classes?
Yeah, so the core lab project of EE16B, which is like an introductory level course that everybody takes who's in the EECS degree, and most people do it like late freshman year or early sophomore year. And so the final project of that course is it's a little car that can drive around, and it responds to 4 different command words that you program into it. And you'll learn to do all of these simple signal processing techniques and all of these simple controls and circuits techniques required to make that car work. It's honestly very satisfying when it's done. And yeah, a lot of people at Cal who are more hardware inclined will get involved in a technical club like Cal Sol or Cal Star. Those two are clubs that are dedicated to building something for contests. Sol is solar cars and Star is rockets. Yeah. Sorry, I'm going to focus for a second on dealing with this.
Yeah, I can add on to that question.
Yeah, please do.
So yeah, George mentioned you build the car. So you're gonna build the actual motor driver circuits. So you power the car from these 9-volt batteries. You have to create the circuit that kind of steps down the voltage and regulates the voltage to a point where you can power the car, power the motors. And then there's also a mic board on the car. So it can listen to what you say, and you write the actual algorithms that can take the raw input of the microphone and process which word you say. So you'd write a basic algorithm that lets you identify the voice signals. And this is something you're going to do within your first year at Cal. If you choose to take 16A and 16B. The first class you'll be taking, 16A, EE16A. The labs in that class, you'll be building you're building a touchscreen out of resistors, which is pretty cool. You also, there's other labs where you learn how solder and build other types of circuits. There's also a lab where you kind of identify the location of a microphone based off a bunch of speakers. So there's an array of speakers set up in a circle, and then you place your microphone somewhere in that circle, and you write an algorithm to detect the location of the microphone just based on the sounds it hears, which is pretty cool. And so like that class is focused a lot on linear algebra. So you're using matrices and whatnot as like the mathematical tool behind these algorithms. If there's like other questions people have,
Yeah.
if you could like send those in the chat, I can try and answer those. Oh wait, George, is everything working on your?
Yeah, it looks like it's
Good.
working again.
Okay, you have the.
Yeah, guys, don't worry if we haven't gotten to your question yet. We have an entire hour dedicated to that coming up. And so, because things have been going slow, I'm gonna try and polish off this LED part of this demo, and then we can move on to the software-defined radio bit. And so, next thing we're going to talk about is how we can read information that's coming through this setup on the other side. And so on this other microcontroller, it's running software which is able to identify the lengths of pulses in some incoming signal to one of its digital pins. And so we're going to use that here to recover the time over which this indicator signal is up. Like the signal that's coming off the comparison of the light-based voltage to our the threshold that we set earlier. And so what this code that I've written here does is it reads in some sequence of pulses and populates an array of outputs with the estimated times that the pulses were actually active for. And it's specifically set to so if we were just doing that, just noting the times between transitions, then we could easily run into a problem, which is actually a very common problem in signal processing of not knowing when you started, basically. If we just had some array that's populated with transition times here in this example, then we would have no idea if the first one was up or down. But in more complicated modulation schemes that a more practical communication system might use, that's actually an even broader problem, which is generally solved by transmitting some known header first. And that enables your receiver to kind of match, since it knows that header, that shape of something you're going to be transmitting at the head of a signal. That means that the receiver can match that timing in order to recover the timing that the transmitter is trying to operate on. And so here that's done through this statement, idle state false, which just means that this receive chain will always start on the low end of this pulse width modulated signal. And so we start reading pulses. We let them read in until we've filled up this array and tell it to stop. And then how do we extract the analog value that we were actually trying to transmit? We've collected some collection of pulses. So let's average all of the ones that should be highs and also all of the ones that should be lows. And so transmitting. And so here, these numbers are in units of microseconds, by the way. Seconds times 10 to the -6th. And so we can see here that the average low pulse after we've successfully started up this receive chain is around 2 milliseconds long. And the average like high pulse is going to be 8 milliseconds long. So adding those together, we can recover that. Oh, right, whoops. Yes, these are the highs and these are the lows. And so that is a little bit off from the 20% duty cycle that this is currently set to. But like, it's off by an amount that we could resolve it compared to some other distinct groupings of things we might want to like read over this PWM. And so as an example, let me change this duty cycle to now 60%. And so now we see that like these values are closer to like 40 by 60, which is actually that's kind of weird. Huh. Yeah, that's interesting. So if we go back to the 40 duty cycle, we can see yeah. So interestingly, there's kind of like a very consistent, approximately 350 microsecond offset on this timing that between the pulses that we've discovered, or, pardon me, that we've recovered. So you could probably use that in order to actually recover these pulse timings much more accurately and be able to distinguish between things that are a lot closer together. But let's say we're very dumb engineers. Let's say we have no idea how to do that. We can still recover duty cycles down to quantizations that are greater than this offset. So like at this frequency that we're transmitting at right now, and changing duty cycle by 10% will change these pulse timings by approximately half a millisecond. And so that actually overwhelms this known offset. So that means that like in general, we can resolve things. So now that we've gotten here, I'm actually going to switch over to talking about software-defined radio. But I'm definitely open to taking some more questions about this while we're switching over. Ayush asks, what is threshold? What's the threshold? So that's what I was talking about with respect to the like comparator job that this circuitry is doing over here. So I can manually set a threshold of like what's currently going through this photodiode, which this circuit interprets as light or not light. So I'm not going to need this for this part. But this is connected. No. Okay. So getting power. I apologize, friends. Please give me one moment. Okay, there's power. And so for this section of the demo, we're going to be doing some stuff with software-defined radio. Software-defined radios are they are basically exactly what they say on the tin. Radios that can have certain specifics of their operation configured in software. And so the salient parts of this setup are the SDR circuitry itself, which all lives inside of this USB dongle, which is connected to a Raspberry Pi and a speaker, which I'm borrowing from a course that I'm currently in, EE123, Digital Signal Processing. And this is actually able to hear the radio spectrum because it's connected to this antenna here. And this is just a simple little dipole antenna. But when electromagnetic waves are incident on this line here, they excite some electric current into the specific oscillatory mode that those waves have energy in. And that, those waves around some point that you're interested in exploring in frequency space get sampled by this, everything inside of this USB dongle, and then read out into our Raspberry Pi here. Oh, huh. You guys can't see that, can you? Okay. This should be more visible now. But yeah, sorry about that. I did not realize that my video feed was getting cropped. But yeah, so I was talking about how this receiver chain that we're going to be using to listen to the radio, it includes this dipole antenna, this dipole antenna, pardon me, which so this dipole antenna, like I was saying, when electromagnetic waves are incident on it, it excites some current, which then can get read out by this dongle and then into this Raspberry Pi. And I'll mention that this demo is based on actually a lab that I did for a class, like I mentioned, EE123, Digital Signal Processing. And so on this Raspberry Pi, we can run a Python interpreter, which is able to, oh, I guess we're not connected here. Give me a quick second. Not that show. Oh, while we're paused on this, Germer, I see your question. Do students generally use Windows, Linux, Mac for labs and projects? So I'm noting the phrasing of your question for labs and projects. And a lot of students use pretty much any operating system that you can think of for their for their personal computers. I've got Mac user friends, Windows user friends, fellow Linux users. Parth, I'm not using as much BSD these days. My home server is still on it. But, so like, the thing about that is that for projects in a lot of classes, you'll want to have like some more standardized setup that like course staff are able to help you debug. And so that means that like, for say like this signals processing course that I was mentioning I'm in, we're all distributed for the duration of the semester, these Raspberry Pis, which have a nice standardized Linux environment set up on them that you can do these labs on. And like for like the operating systems class here at Berkeley, you're strongly encouraged to do things in a virtual machine that you can run on your computer, whatever it's running, or like on the school's instructional servers. But that means that like for projects, you will usually, I guess I'd say you're generally not set up in a way so that you're limited by what you're personally using. And one quick second. Notebook, new browser. All right, it seems like we are back now. I also see that it's now 2. I apologize for my technical difficulties slowing down all of this. But so in this demo, we're going to talk some about like a much more practical communication protocol than the very simple one that I was showing you earlier. And that is FM, frequency modulated radio. So the core of FM, is that like you have some specific frequency of wave that like your station is supposed to be transmitting at. Say like for the purposes of this demo, we're going to be listening to some commercial broadcast FM at 96 megahertz, which is here in Santa Barbara, it's a cool little rock station. Or no, sorry, right, I was reading that wrong. We're going to be listening to 103.6 megahertz. This is the sampling frequency. This is the rate at which samples get read into this setup. And so the way frequency modulation works is you have some specific frequency that some carrier frequency that you want to encode your information around. And you like twiddle around with the frequency of like a cosine wave at that specific carrier frequency. And so like, sorry, was somebody starting to ask a question there? Oh, never mind, I will move on. But yeah, so frequency modulation works by like very slightly changing around the frequency of a cosine wave in order to capture data that you want to transmit. And so when we listen to like, we graph in spectral space, the basically energy that's being transmitted by this commercial radio station near where I live, we'll find that like around its carrier of 103.3 megahertz, it's putting energy a little bit further out into the band. And that's because, well, part of it is because like the actual sounds that it's trying to transmit are a little bit off in frequency, or make what it's transmitting a little bit off in frequency from like that specific carrier wave. And so in order to process this, we are first going to like cut out all of this dead space that like nothing interesting is happening in. And this is called a low pass filter. It's like it's a mathematical object that exists in discrete time that we can kind of like pass this frequency space representation of our system, of like our signal through, in order to kill off all of these regions that we don't care about. And when we do that, and we also downsample to like, first of all, just have a little bit less data to deal with, and also to like reduce the, pardon me, yes. So here we are all passing that filter over this data. And so like, this is the frequency space representation of this filter. It passes through frequencies that are like in discrete time, close to, that are low in this discrete time representation. This is not like the continuous time frequencies that we're like sampling over. These are frequencies like in discrete time. And we can pass that filter over this data and zoom in on it a little bit. And we see that like, we notice these points where there's certain distinct frequency offsets that are visible in this band. And we'll notice more about what's causing that once we demodulate it. And so we're going to just like very slightly rescale this data to avoid having like zeros and cutoffs, which is just a nice little change you can make. Oh, whoops, I forgot to rerun these cells since we started this, restarted this part of the demo. Okay, yeah. And so like, now the question becomes, how do we get information out of these deviations in the frequency? And so if you've taken a calculus class, you probably know that when you take a differential of a trigonometric function, you get like a phase shift of it times the current instantaneous frequency. And so that's the principle that we're going to exploit. We're going to make a filter now that effectively takes the derivative locally in time of this signal that we're receiving. And then we're going to multiply it with an appropriate phase shift of itself in order to cancel out that part of the derivative that just looks like the original signal. And by doing that, we'll extract a signal that looks like the instantaneous changes in frequency of what we're receiving. And so I'll give this a second to process. And yeah, one thing you'll notice is that like within a given commercial FM signal, there are like a few different groups of things that these commercial stations will do. There's a pilot frequency, which is always at about 20 kilohertz above the carrier. And that's like this very solid line here. And that's used by hardware receivers that need to lock very nicely to the actual frequency that this station is using to help them like lock specifically to the frequency that data is modulated into. But in this case, we're not using that because we have knowledge beforehand that this specific station that we want is here, and that we have a good ability to generate in this SDR chip a local oscillator that we can use to demodulate it. And you also see that there are like these regions above and below that pilot wave. And that's because most commercial FM stations, they're transmitting stereo. They're transmitting like two different channels of whatever data they're trying to put out there. Like basically left and right. But so for the purposes of this demo, we will just demodulate. But like, yeah, I guess I wasn't clear about that. There's, when you're transmitting stereo, in general, you don't do like independent channels for left and right. You'll instead do like a left plus right and a left minus right channel. And so what that means is that like this lower region here is directly extracting the like what's called the mono, which is all of this information, basically the average of the left and right channels. And so that means that like that's because this was developed historically before the time when people were interested in doing the stereo bits. And so like we can have a compatible system which demodulates just this mono region. And so in order to do just that, Nehas, I see you're asking at what time does the panel start? It starts soon. I will be finishing up in just a couple of minutes here. And so we're going to like filter out using another low pass filter just this specific, like the mono channel of this frequency modulated radio. And we'll see that like it's band limited to around 16,000 hertz above the fundamental frequency of this carrier. And if nothing went wrong, we can now play some audio. Can you guys hear that? Let's see, how long will it take Twitch to copy strike us? All right, and yeah, so that is the end of my pair of demos. We will presently be transitioning over to panel mode. So if any of our particular hosts want to talk about this, maybe we can pause for a couple of minutes. Or
yeah, sweet. Thank you so much, George. Yeah, thank you so much. So we're gonna do the panel on the same call as this Zoom. We're not gonna use the Twitch stream anymore, so you can feel free to leave the Twitch stream. And we're gonna have the HK members here answer some questions. They're gonna turn their video on. And we're just gonna have like a live Q&A. We're gonna go through and do like a kind of a student panel. So if people have like questions, I know there were some questions earlier that did not get answered. You could ask those again. and we can try and address those. We have like a full hour for questions and like going through the panel. So it should be more than enough time to get everyone's question. So if the HCAN people here want to turn on their videos, sweet, that would be, and then Caitlin, you could probably stop screen sharing. Awesome. So maybe let's go through everyone one by one and just like give a brief introduction, like your year, stuff you are, like classes you're taking, stuff you're doing on campus, maybe why you chose to come to Berkeley. And yes, there will be a recording of this demo posted later. So Parth, do you want to start?
Sure. Hi, everyone. I'm Parth Noble. I'm a third year Berkeley. I do a lot of work in firmware and in some of the more pure math parts of the field, like system theory. And I'm very active in the Model United Nations team at Berkeley. I do speech coaching for them, and I used to be an officer for them. And I really like Berkeley because it's this huge, diverse school, which has a lot of really interesting like legal classes that I've taken at the law school and on campus. And I've been also having a great time learning so much from all the technology work that's going on here and the research on campus.
Naomi, do you want to go next?
Before you guys go, let me stop recording and re-record.